Any questions before we get started? The next homework has been posted. The first part of today, we're going to talk more about linear regression. So we kind of touched on it at the end of yesterday, that it's actually a little bit more powerful of a tool than we saw when we started. We can actually fit more complicated functions from just a line with a few constraints. Yesterday we saw that we could fit equations that look like this. And the betas were the things we were solving for. Turns out that the way we solve for these betas works for more complicated equations. So we can actually fit betas for anything that looks kind of like this. So we have our constant term. So we have here this thing that I'm multiplying by the beta by can be any function of all of the input variables that I have that I want to consider. This f could be what we saw yesterday. We saw just like f1 of x1 equals x1. That's what we used yesterday. I think at the end we saw an example where it was like x1 times x2. Or maybe we'll see that today. I can use whatever complicated function I want here. And as long as my betas only show up in front, then I can solve this really efficiently no matter what my x are. So this is called multilinear regression. We have many linear coefficients, that's what these betas are, that we're solving for. Right? We can solve for them all very efficiently and fit all sorts of crazy functions. So one thing that we can't do, so if I had I tried to use like beta as a power, can't do that. If I tried to take like the square root of a beta or the sine of a beta, can't do that. So these things don't work. All right, my betas basically can't show up inside of these f's, but otherwise I can do pretty much whatever I want. Okay. Yeah, we can use the same tool we talked about yesterday to fit much more complicated functions if we kind of think we know the shape of our data. So if you remember from calculus, when we're doing this, yeah.
Just quickly, was B0, is that B or B?
That was B before. Just the intercept term.
So B1 is X.
B1 would be, so yesterday I think we wrote this as B plus AX. Okay. So the assumption we're making here is that our data matches some function y of x, which isn't always true, right? If my data looks something like this, then there is no function y equals f of x that describes this. Right? So I need some other way of trying to model or understand my data. But as long as my data looks like some function, right? Then if I had infinite understanding, I could represent this. So since we can do whatever complicated stuff here, if you think about it a little bit, think back to calculus a little bit, we'll see that we could actually come up with a basically perfect multilinear regression for our data, which seems like it might be a attractive thing to try to do. So if you remember from calculus, I left out the calculus part, but remember, any function can be written as a sum of these polynomials. Right? So if I just keep adding powers of x onto infinity, then I will exactly match any function f that I want to, as long as I choose these coefficients correctly. Right? So you might be tempted to say, okay, well, why don't I just add as many terms as I can, and then my function that I approximate with is going to match my data basically perfectly. Right? And it turns out that that's usually a really, really bad idea. Right? So we're going to match our function better and better and better and better. But our approximating function that we come up with is going to be less and less and less useful. So let's take a look at a simple example to see why that's the case. So let's say my data looks like this. If I do a linear regression on this, right, it's just a line. It approximates the data pretty well. It doesn't go through all the points. Right? I think this is a pretty useful approximation, right? It closely matches the data, especially if we assume that there's some error in the measurements that we're taking or whatever. Right? But for this particular data set, I could keep adding terms, and eventually I would get a function that goes exactly through every single data point. So my R squared equivalent, which we'll talk about in a sec, would say that this is perfect. We're capturing every single bit of our data. If we plug in an x to our equation, we'll get out exactly the y that we measured. Right? Any ideas what an equation like that would, or what a function that I fit would look like if it went through every point and I did something like that? So here I have 1, 2, 3, 4, 5, 6, 7 points. So I think I need to go all the way up to x to the 6th to fit everything perfectly. And what that's going to look like, my marker works, it's going to look something like this. And it's going to go through every point exactly, but it's completely useless. Right? I already knew the values of the points that I measured, and this doesn't give me any useful information about the points in between. So this is an example of what's called overfitting, where we're so concerned about accurately matching the data that we've collected that we come up with something that's totally useless for any other data point that we have to see. So in general, there's going to be a trade-off between the accuracy on our data. So how closely does our fit match the data points that we trained on, and the variance or the kind of wiggliness of our fit. Okay? So the closer that my approximation gets to all my data, the more wiggles I'm going to have to add to do that. And so in general, the less kind of useful it's going to be. So we have this incredible power to add as many terms as we want to, to perfectly nail our data. But most of the time, that's not what we want to do. We want to basically figure out what is the smallest number of the appropriate terms that we need to get a useful approximation. That makes sense. So any questions about the general idea? Okay. Yesterday we saw we talked about the p-value of our coefficients. So that was one of the outputs we got from stats models. Anybody remember what that was describing? Well, that was a p-value 4. What was the hypothesis that it corresponded to? Yeah. So it was basically telling us how likely it was that the coefficient had a value of 0. And so for everything, basically, yeah, let's measure kind of flatness. So if my coefficient's value is 0, or the distribution is kind of close to 0, probably it's not very useful to include in my model. Right, so I probably actually want to get rid of those terms that are probably 0. Right? When we're talking about multilinear regression, there's kind of 2 related topics that we'll encounter. One refers to kind of all of the coefficients together, and one is kind of a per coefficient kind of thing. So the p-value tells us the probability that a particular coefficient is 0. A related thing that we get out of the linear regression fitting tools is called the F-score. And the F-score tells us, so the F-score is related to a hypothesis test that all of the coefficients are 0. So the hypothesis, all coefficients are 0. A large F-score means basically we want to reject the whole null hypothesis. Okay. So if we have a large F-score, that means there is a linear relationship here. If it's close to 1, that means that actually the coefficients might actually be 0. So that's, in addition to the R-squared value, this is another thing we'll look at to kind of talk about the quality of our fit.
What's considered a large F-score?
So it comes from a distribution. So in addition to the F-score, you get the probability of the F-score. And so we could use the same sort of significance cutoffs that we use for the p-values. So if the probability of the F-score is less than 1%, then you could conclude that the coefficients are not all 0. Okay. So I don't know, this doesn't seem like the most useful of things because probably there's going to be some relationship between some of the terms that we have in our data. But this is actually useful for helping us determine which of our terms are useful. Okay. So basically, what we compute something like an F-score with for each coefficient, kind of leaving everything else out. Okay. And that's actually where the p-values that we saw came from. So the per coefficient p-values that we saw yesterday, they actually come from computing the F-scores, and that's how we get those. So we'll go through some examples where we're looking at these to decide basically what how many terms we should include in our models. So that's kind of a numeric or an analytical way of analyzing how good of a choice our model was. But there's actually another pretty clever approach that works well for more complicated models where we can't compute something like this easily. And so it's where it's hard to like compute one number that says, is this a good model or not? And this is called cross-validation. So the idea here is that we split our data that we have into two halves. And we split it into training data and testing data. So we just cut it up by some proportions, and maybe we go, 80-20 or 50-50. And then we fit our model using the training data. Okay. So when we do the math to do our regression, we only look at this data. Okay? And then we just measure the error of the testing data when we're done. Okay. So the idea here is if we came up with, if we overfit our data, right? If we came up with, some crazy function that looks like that, if the data really is just kind of a line through the middle, this is going to have really high error when we test new points that are, slightly different from the ones we turned on. Okay? So if we overfit, we'll definitely detect it here. We can also detect sort of underfitting. So maybe our model was not complex enough, right? We'll have pretty big error on our testing data and our training data in that case. It doesn't fit either particularly well, right? That means we're probably underfitting. And so by looking at, by doing this split, we can kind of, we can use that to guide us to an appropriate model.
How do you determine how to split your data?
Usually it's random. So you say, I want this proportion, and just randomly choose. So there's functions and the libraries we're using that will do that. Okay. So cross-validation is a really, really important and like ubiquitous tool. All sorts of machine learning methods do stuff like this, where they train on some set of data and test them. It's important that you keep these separate, right? If you add your testing data and use it to influence your training, then it's also training data, and so now you're overfitting to more data. Okay? So we want to make sure that we keep these separate. But yeah, it's a really useful tool. So what are some of the downsides of doing this cross-validation or doing this splitting? Or when might it be tough to use? Yeah, if I don't have that much data, it could be tough. How come?
You might not be able to create, I guess, a real good feature path.
Yeah, if I like barely have enough data to train on, I can't, if I just throw some of that data away and don't use it to train, then, you know, I probably am not going to make a good model, and I'm going to have a tough time evaluating if it's good or not because I don't have enough data to test with. Okay? So I kind of need more data to make this happen. In the modern world, I think the problem we always have is too much data, so this tends to be a pretty broadly applicable technique. But yeah, it does mean, you know, I'm not using all my data to train with, so my model might be missing out on some of that information that my testing data would have provided in training. Cool. Any other questions? All right. Well, let's take a look at some examples. Cool. So we're going to take a look at another couple of examples. So we looked at the advertising data yesterday, right? Okay. So I think, did we get to or we use this more complicated model at the end? Yeah. Okay. So yeah, this here we're fitting basically our 3F functions that we were using are TV, radio, TV times radio, right? You know, even though this is a more complicated thing, because we're just looking for a beta to stick in front of it, we can fit this, and that's totally fine. Okay. So if we look at the F statistic, right, this is telling us basically is it likely that all of these coefficients are 0? And we see the probability of that is 10 to the minus 146, so very unlikely. Yeah.
What exactly does it mean again if all the coefficients are 0? That feels like that to me would mean your model is around.
Yeah. Mm-hmm. Okay. So that's, yeah, if I had an F statistic of like 1, that would say basically there is no relationship here with the variables, with the variables that you provided. Cool. So, and if we look at all of our terms, right, the p-values are all very small, meaning that, again, it is very unlikely that these coefficients are 0. And these come from computing something like the F-score. Cool. So yeah, our R squared is very high, so we're explaining most of the variance of the data. These are good, right? So we have a model that is accurate and is not overfitting. So again, we can look at our model graphically. So this is an example of overfit data, right? Like we were talking about yeah, on our training set, we have 0 error. We go through every point exactly, but obviously the blue curve is not the least bit useful for making predictions, right? The fact that going from this point to that point takes you up here, you know, it's useless. It tells you nothing important. Okay. Yeah, there's kind of 3 things we're trying to trade off. So we have this bias, which is basically what is representable by our model. Okay? So if we're just trying to fit a line, and our data happens to be, you know, a parabolic thing, right? We're going to have errors because our model can't represent that. We have variance, so that's kind of the wiggles, and then we have the irreducible error, which is, you know, our measurements had noise or whatever. And so when we choose the model, basically we can choose how we want to trade off these 2 terms. Okay? We can either add, when we reduce the bias to capture more variation of the data, we add more variance and more wiggles. And so we're trying to find the right balance there. Okay. So we'll take a look at another data set. So this is a bunch of information about cars. We got the name, the year, miles per gallon, other stuff like that. Pretty big list. Pretty old stuff. So if we look here, we have 400 cars worth. Mean miles per gas mileage is actually higher than I would have thought, given the number of cars from the 70s in here. Number.
Like 44 miles per gallon. I don't know what is that kind of car.
The max 46 miles per gallon.
Yeah.
Would be like a hybrid, or even like a little car. I think, or like the Toyota Echo or Yaris or whatever was pretty high.
My AV C is like 49.
Yeah.
Pretty much. I don't have to tell sorry.
This was a little surprising to me. The mean number of cylinders was 5.5, so we got a lot of V6s and V8s in here. The heaviest car is about 4 times bigger than the smallest. Interesting. And these are mostly older cars. In any case, so we're trying to look at this data. One thing we might be interested in is power efficiency trade-offs. So horsepower versus miles per gallon. So we have a plot of that here. Okay. So does it seem like there's a relationship between these 2 variables that might be worth modeling? Yeah, I think so. So we got some outliers, but yeah, it seems like as you increase your horsepower, you decrease your efficiency. It's a linear fit. This looks like it's a linear kind of thing. Not really, there's some curve here. It's a linear model, probably isn't going to capture everything we want. So we're going to look at basically a few different models that we could use here and see how they compare. Okay. So basically what we're going to do is we're going to do the Taylor series thing, and we're going to just try a few different powers of horsepower. So we're going to try a linear plus a quadratic plus a cubic up to some power m, and we'll see, which of these models is the most appropriate. So the higher the m, the more terms we add, the more we're going to match our data, right? So each one of these fits is the best fit for the number of terms that we have. So if I add a term, things could absolutely never get worse, right? If I add a term and that term is not helpful, then the coefficient will just be 0, and I'll get the same thing I had before. Like, there's no way I could ever get worse by adding terms. And in general, I will get a little bit better each time. Okay? But there's diminishing returns, right? So as I add, 2 terms, maybe things get a lot better, and then after that, it really plateaus a lot. Okay? So we want to figure out, okay, how many terms should I include before, I'm just making my model needlessly complicated. Okay? So we're just going to fit formulas. So we have the linear formula, the quadratic formula, all the way up to the 4th degree polynomial. And then we're just going to plot all these lines and see how they compare. And so if you look here, the linear one is really not very good. The quadratic one looks okay. The cubic one I think looks pretty good. The 4th degree one starts to get a little weird. So just from a glance, to me it seems like the quadratic or cubic are maybe the best ones. Yeah.
What is the I parentheses?
Yeah.
Is that just the weird?
I don't know if that's actually necessary or not. I was trying to look at this. So this is it's using. Yeah, I am not entirely sure exactly what it is. What it is specifying. So the so it looks like the this language called Patsy, and so yeah, if you want to do more complicated formulas, then this would be the place to look. Unfortunately, that I is extremely unsearchable. The identity function? Oh, I see. So this is to group something into a term, I guess. Yeah. This is the kind of thing where probably I would try it without the I would get an error, I would Google that error, and on the first Stack Overflow it would say, oh, you need to wrap that in I. I think is how this type of development goes. Right. So we have our various degree models plotted. I think it's obvious that the linear one is bad, and it's maybe not obvious from a glance which of the others is the best. But I think we also see that they're all pretty similar in here, right? So like through here, through the kind of the heart of our data, adding more terms doesn't change stuff much. So we look at the R-squared value for these. We see that, yes, when we add more terms, we increase our R-squared value. But there's a pretty big jump from 1 to 2, and then a much smaller jump for the next ones, right? So we're explaining less of the variation in our data, or the amount extra of variation we're explaining in our data decreases pretty rapidly. And there's an upper limit on what we can do here, right? We're not really going to be able to fit a line that goes through all this data, right? So there is, an R-squared of 1 is never going to happen here. So yeah, I think it looks like we've hit diminishing returns based on R-squared value. And if we look at the summary, So here, this is the 4th degree one. And what we see is our F statistic is good, so we, there is a relationship there. I can't think of a situation where you would think to do regression and you would get an F score that was low. Your data would have to be just totally uncorrelated, I think, or you'd have to just pick the worst possible model. I think most of the time the F score doesn't tell us that much useful stuff. But if we look at the coefficients, we see our p-values are pretty high. Okay? Again, so these are basically the probability that this coefficient could be 0. Okay? So we see that these are all pretty high, which probably means we're overfitting or we're using too many terms. Okay? So this is just kind of a good model, right? Our p-values are generally going to be pretty low. Another way of thinking about this is our R-squared value tells us that we're matching our data. The high p-values mean basically these terms could be explained by the other terms as well as they could be explained by themselves, if that makes sense. And so it's kind of saying, like, if I took out the linear term, the other terms would still capture most of the data. If we look at the quadratic version, so where you just have 2 terms, our R-squared value again is almost as good, and this time our p-values for our coefficients are much lower, which means basically we need them all. So we can one way of thinking about this is Occam's razor, which is the simplest explanation is usually the best. So in this case, quadratic is simpler than a degree 4 polynomial, so that's probably a better model. So that's how we can use kind of the p-values to help us decide between various models.
If you did the M1 summary, it would obviously show a lower R-squared. But with its p-values, it also should be pretty close.
I would expect so. So R-squared went down by like 0.08, p-value 0.
At this point, you just have to look at it visually and compare it to higher order.
Yeah. Yeah, so in this case, I mean, so probably the first thing here I look and I say, that doesn't look linear to me. And so I would say, okay, probably need a higher order term here. And then to sort of confirm that, I would look at the p-values and the R-squared values to confirm.
This first order, would you ever get a p-value that's, I guess, 5? So I guess there's 2 discounts in that relation.
If you had a constant, so if it were flat data, then you would get a p-value of 0 because, or you'd get a high p-value because that coefficient corresponds to 0. It's basically not needed to explain the data. Cool. Any questions about that? So that makes sense. Right. So we'll take a look at another another data set and do some cross-validation. Okay. So here, yeah, the idea is basically split our data, train on one set, look at the accuracy of both sets, right? And that'll tell us basically, are we underfitting or overfitting our data? So what are we doing? Oh, so we're going to use the scikit-learn instead of the stats models for this. So scikit has test train data split. So we're adding basically our complicated terms. We're adding them to the data ourselves. And so we're we're adding new columns to our data, which is basically horsepower squared cubed to the 4th to the 5th. So the stats model is where we like write out the formula. It'll compute those as they're needed. So in order to do the fit, we actually have to compute horsepower squared and all that stuff. Stats models does that for us. Scikit-learn doesn't. So here we're just adding those. And then we are grabbing, we're taking our all those inputs, so horsepower squared up to the 5th, and we're sticking that in a 5 by, or an n by 5 matrix. Okay, so we have, we're going to have one column for horsepower, one column for horsepower squared, one for horsepower cubed, and so on. And then our y's are going to be just the MPGs. So the how many people have done matrix math stuff before? So another way of describing what we're doing here is we're trying to solve this matrix equation, x times beta equals y. So this beta is, these are our coefficients, these are the x's are our inputs. So we're just adding up the inputs for each row and scaling them and trying to match the y. This is how things are working under the hood. The way that scikit-learn takes its input is you actually provide these matrices as matrices, and that's how they work. That's what's going on here. So our x is just, so here we have our horsepower column, our h squared, h cubed, h4, and these are our, so this is just another way of thinking about what's going on. Okay. Cool. So we'll just plot the first row. So that's our horsepower and our MPGs. Those are the same plot we had before. So we're going to do our fit. We're going to fit the first m columns. So we'll fit a linear, quadratic, cubic, degree 4, degree 5. And then we're going to use the predict. And so you see we actually get out. So this is the same thing that we got before, except we're just using the scikit-learn framework instead of the stats models. So these, the linear degree 2, 3, 4 are exactly the same. We added a degree 5, 1. You can see how just this one is going to be pretty bad if we're looking outside of the range of data that we have. Now that we kind of have this set up, we'll look at doing cross-validation. Okay. So we have this train test split function. So these are our x's, our y's, and we're going to set the testing size to be 90% of it. Okay. So we're only going to train on a random 10% of the data. Okay. And then, so we'll get, we're basically picking rows randomly out of each of these matrices to go in our data sets. And so you'll see when we look at the shape, we'll get 90% of the rows will be in our testing data set. Okay. And so now what we're going to do is when we fit this, we're only going to look at the training data. Okay, so we're only looking at training data. And then we're going to look at the accuracy on the training data. Okay. and we'll look at the accuracy of the test data. So these both tell us stuff, and then we'll plot. And so the red ones are our testing data, or sorry, our training data. So these are the points that we're using to fit. The curves that we found look pretty similar to the ones we found before, right? So even though we only used 10% of the data to train on, we still got pretty close to what we had before. And now let's take a look at our training and testing results. Okay, so we're looking at this is the R-squared value, I think, that we're looking at, or yes, I believe this is the R-squared value we're looking at, which is going to tell us basically how well are we matching the data. So we look for the linear model. On the training data, it's pretty low, and on the testing data, it's even lower. Okay. So this tells us that we're probably underfitting. Right, it's because our training data is low, so we probably don't have enough degrees of freedom in our model to actually represent what the data is saying.
You're saying it's low compared to what? Low compared to the other?
Low compared to the other ones. Yeah. So here, when we went to quadratic, we saw a big jump in R-squared for both the training and the testing. This training R-squared is way higher than we saw for any of the models before. Right? Before we got to like 0.68. Here we're already up to like 0.78. Any ideas what's going on there? There's way fewer data points, so it's much more likely that we're actually, capturing them. Right? So we're kind of solving an easier problem here, so of course we're going to do better. So yeah, we have less data to match, so we're going to match it better. And then our testing R-squared is actually slightly less than it was for the quadratic model that was trained on everything, but only very slightly. Okay, so we lost a teeny little bit of R-squared overall by reserving 90% of our data to test with.
I may have missed it. What's the difference between training and testing? Does that have to be the total data?
Yes, so they are, the training in this case is 10% of the rows, and the testing is the other 90%. Once we get up to here, we see that we went to the cubic, our training R-squared improved a little bit. Our testing R-squared actually went down. Okay? So this tells us that we're entering the overfitting range, right? Our training R-squared is of course always going to go up. Our testing, right? If we overfit, the testing is actually going to get worse because we're kind of adding extra wiggles that match the training data, but not the testing data. Okay. So at this point, we're like, okay, probably the cubic is overfitting. It gets worse as I add more terms. So when I go to the 5th degree, right, I would definitely overfit. Yep.
So would you go back at this point and not use the training? Would you say, okay, we probably want second order, so I would do 100% data and get the results slightly better?
It's a good question. I'm not sure what people would do in practice. I guess, yeah, that's a good question. I don't have a good answer. Let's just take a look and see what would happen if we split things. So let's make our test data a little bit smaller, right? So we're training on more. So we do that. And then, I mean, our curves look about the same. Our things look about the same as they did. Right, so it's not, doesn't appear to be super sensitive to the percentage of training and testing data. If we went really far the other way, here it becomes, as it's still, we see this drop off in the testing set accuracy at when we go from quadratic to cubic. And so even with most of our data going to training, right, we still right, we can still see this drop off.
Noise though, right?
Well, the fact that it gets worse, right, is
Yeah,
means
like
we're overfitting.
The fourth degree, it got better right now.
Oh, it did?
Yeah.
Oh.
I thought so.
Yeah, so let's look at this here. Interesting. Yeah, and so I guess part of it is just kind of a luck thing because we're splitting this randomly. Yeah, so this case, when we went 50-50, it was unclear that things changed. I mean, so here when I see that my training data gets basically no better, you know, it's this teeny little increase up the fourth digit, I can say, okay, probably this isn't adding a lot.
So are we supposed to shuffle the training and testing cells if we don't have enough data?
Yeah, so that's a good question. So that is called, we usually call that k-fold cross-validation, which we'll talk about it at some point in more detail. But the idea there is that you take, let's say k is 5. What you do is you would split your data into 5 pieces, and you would run your analysis 5 times, and each time you would use a different 20% as your training data. And so each data point will be used as training and testing in one fit, and then you kind of look at overall, like how stable is it across you know, each of the folds, yeah, so you're kind of reusing your data to make it go further. Does that make sense? And, cool. So, yeah, this is how we can kind of think about choosing a model, some of the tools that are at disposal for doing that. So the next thing we're going to go through together and look at another data set, see what sense we can make out of it. Yeah. So we have this credit data, and what we're interested in is basically we're trying to figure out what affects your credit score and your credit limits. So that's kind of what we're trying to figure out. So maybe you're a financial advisor and you want to tell your client, like, how do they, what should they do to improve their credit score or whatever. Okay, so this is the data that we have. So it's got income, credit limit, credit rating, number of credit cards, stuff like that. So this is what we have for our data. The data types that we have are a float for income, ints for all these things. So education being an int seems to, they have some sort of categorization for this, right? So education of these. So Any guesses what this corresponds to? Be grade completed, although a lot of people that aren't making it to high school. So, yeah, I have no idea. Then here we have gender, whether or not they're student, whether they're married, their ethnicity. So these are all categorical. So the object here means string. So usually when you see object in the data types, the object is string. Cool. All right, so this is our data. So the first thing we want to kind of do is just get a sense for just an overview for the data. So we saw the data types. Other things we might be interested in are the value counts. So for the categorical data, that would tell us how many of each we have, and the describe gives us these descriptive statistics. So this gives us, for our quantitative variables, gives us the kind of data we have here.
Are you going to post this after?
Yes. Yeah. Yeah, so this is up now. So if you want to kind of play along, I encourage you to do that. So our gender looks like we have pretty close to even split of men and women. And so it looks like we have not that many students, a lot of married folks, and mostly white people. So this just kind of gives us a sense of what our data looks like, right? And now we can kind of get ready to start exploring our data. Cool. So this is the data. The income data is actually not really, looks pretty weird. So the mean income is 45. So our units are kind of messed up here, right? Especially relative to the credit limit. Right? The fact that the credit limit is 100 times bigger than the income is probably wrong. Right? So what's probably going on here? So this is not actually the income of people. Could be extremely predatory and dumb lenders. Right? What's more likely? So the income is probably not $45, but 45.
45K.
Probably $45,000. Yeah. So probably we just want to multiply these by 1,000. Okay? So we can do that with map. We can do and then for each one of these, we want to multiply by 1,000. So this is not going to change anything. This is just going to give me back a new series, which looks a little bit more reasonable. If I describe it, I see the count is the same, and now the mean is 1,000 times greater, which makes me think that I did it right. So now I'm going to overwrite. So now I've updated it. Cool. So we had to do a little bit of cleaning for our data to get kind of the units to be what we thought they should be. So we'll look at, so now we have all these fields and we don't really know how they're related. We'll look at two approaches for kind of understanding relationships between our columns. So one is to look at the correlation coefficients. So we talked a little bit about, we talked about correlation with the descriptive statistics, or this is just a measure of how two variables change together, right? So we'll look at that numerically. And then scatter matrix it basically draws scatter plots of each pair of variables, and so we can visually kind of see if they're related or not. So that's the next thing we'll look at. So we can use the correlation function, and that'll tell us how things are related. So everything is correlated perfectly with itself. Not a surprise. But let's look at some of the other. Anything pop out at anybody here? The limit and rating seem to be pretty strongly related. So it seems like maybe the credit limit is a simple function of the rating, or vice versa. What else sticks out? What other ones are pretty high? The balance is strongly related to your credit limit or your rating. And so the amount of money you owe on your credit card is related to how much they trust you with, I guess. Are there any that don't seem to be correlated with anything that is surprising or expected? So age looks like it has some correlation with income. So older people make more money, I guess. A little bit of correlation here. Education is kind of surprising. Education looks like it has basically no correlation with anything, which I probably would not have guessed. Income and balance, maybe that. I guess the more money you have, the more money you can float on a credit card. Right, so this is one way of looking at it. The other thing we'll look at is the scatter matrix. The semicolon says don't print the output, so I don't really care about all the noise. Here is the scatter matrix. So down here we have the histograms of stuff. Here it's very obvious that the credit rating and credit limit are closely related. And the balance as well. Yep.
On the table above, it didn't have any of the object.
Correct.
Yes, no.
Yep, so this is only going to look at the quantitative data.
If we change that to a 0, 1, or
we'll take a look at the categorical stuff a little bit later. Yeah, if we change those to 0, 1, they would show up here, but it's hard to make sense much of those when there's so many repeated values. But that's, yeah, we'll take a look at categorical data in a little bit. Yeah, cool. So, yeah, it looks like basically if we figure out either the credit rating or the credit limit, we've figured out the other. So, we really need to only look at one of them. And we think, balance might be important. Income might be important. Okay. So some observations. Limit and rating are correlated. income and limit related balance. So yep, good point. No categorical data. One thing we could do is we can look at the categorical data with histograms, just to kind of see what data we have here. Cheat like the last year's notes.
We use the other 0, 20, 0 or something.
Oh yeah, I can do that. So we'll pass the axes as a. We can do the same thing for students. Married. And ethnicity. So. This doesn't really tell us the correlation, but it gives us a sense for the frequency of the values. So I don't know. It's not obvious from this what any of those relationships are yet. If we converted them to numerics, then we could look at the scatter matrix of the correlation, but we'll skip that for now. Okay, so let's start by doing a linear regression, just to see exactly how the credit limit and rating are related, because we saw that they're strongly correlated. So we think that limit is a function of rating. Make sure I got the. So yeah, this error is terrible, and that's better. Okay. So now we have this simple model. So we're just looking at limit as a linear function of rating. R squared is very, very high, right, which shouldn't surprise us given that our data was, you know, a straight line. Our intercept is negative 500. And it looks like our rating is, coefficient is 14. So one way of saying, thinking about this is basically the rating, or sorry, the credit limit is 14.8 times your rating minus 5%. So this appears to be the formula that so that's what this tells us, and yeah, we can see from our R-squared value and our p-values here that yes, this is a very good model for these two variables that are related. Yep. So this tells us that these are basically the same variables, so we're just going to ignore the rating because they're the same thing. So let's take a look at. So maybe take a couple minutes with your neighbors. Come up with a few different models for the credit rating as a function of everything else, or the credit rating as a function of other variables, and we'll get back together and talk about what models we saw. So go ahead, play around with a couple, see if you can find, see what models make a lot of sense.
Can you scroll back up to your second?
This one?
Oh no, I'm thinking of the other.
Yeah.
In the credit data.
Oh, yeah, it's easiest if you clone the repo and then you can.
Okay.
Yeah. So yeah, you can look at these on GitHub, but you can't run anything on GitHub.
Do we need the stuff that you've done before?
No, you shouldn't. Just the loading stuff, which I think is already in there.
Are we getting realization?
No, but actually do it. Yeah, so I think you should only have to run this cell and the imports. I will say the homework is pretty similar, so getting the practice now is probably is a useful thing to do.
That's definitely.
You may also want to do this scaling of the income, it shouldn't matter. It would just affect like the scale of the coefficient. But might be you might add that in. So one strategy I use playing around with this is to start with a model that includes everything, and then start removing terms. That's one way to approach this. So, I might start by just including everything, throwing the kitchen sink at it, seeing how we do. And this does seem to be a pretty good, pretty accurate model. But probably not everything is all that helpful. So which one of these terms probably should I get rid of? Probably the number of cards, right? High likelihood that it's not a useful thing, so just get rid of that. Looks like education, not that important. So, not sure what you all are doing here. Age, also not that helpful. And again, our R squared is basically the same as it was. So get rid of the age. Same R squared value. Now these are both look like they're important. So it looks like a model. My rating is pretty well represented as just a linear, a multilinear model based on income and balance. Any questions about? So do a little bit of model exploration. So we did this kind of exploratory analysis to kind of figure out what might be important, and then found ourselves a model. So income and balance are best predictors. The other ones don't matter so much. So the categorical models, if we want to use them in the regression, they have to be numeric, right? So we'll convert those into numeric variables. So we can use map again. So this time, so we used a function before with map. You can also pass a dictionary. and it will look up the values. So I'll say that female 1, male 0. So I guess. So the I don't know if you can tell from the it's hard to tell from this, but apparently there's actually a space before male for whatever reason. I think actually when we do this mapping, we have to stick a space in front. Yeah. Terrible. So we could have done a little bit more data cleaning here. But so now we have so now we can add a new column. For the gender number. Let's do another fit here. So let's see if we can see if income is a function of gender. So apparently not. We have an R² value of 0. And so it looks like income is not gender is not a good predictor of income. So, and for this data set, it appears not to be. Let's maybe, I'm curious, let's do a little scatter plot here. That doesn't seem right. So for this data set, it's a little bit hard to tell because there's overlap, but it would appear that the distribution of income by gender is maybe not so important here. So if we wanted to know a little bit more about the distribution by gender, how could we do that? How could we plot to get more about the distribution here? So the scatter plot's not all that useful. Yeah. Is there another type of plot that might be useful? The Boston Lister might be useful. Let's try. So we'll do box plot. spot. And then we'll do, we'll group it by gender. So yeah, the distribution of these two is seems to be independent of the gender for this data set. So we have confirmed that for at least this data set, there does not seem to be a significant relationship between gender and income, which I think we can all feel good about for this particular data set. Okay. So the last thing we'll talk about just briefly is the multiple categorical variables with multiple categories. So we could assign a number to each of these categories, but that's probably not very good for our regression. So if I tried to use this ethnicity number in a regression analysis, what's wrong with that? It's basically ranking my categories. So in this case, I'm deciding the relative value of the races of my subjects. Probably not a good idea. So what we usually do with these types of categorical variables is we make a column for each category and assign it 0 or 1 if it's true. So basically, we would, for the ethnicity, we would make Caucasian, Asian, African American columns. So the function that does that is get dummies. So this gives me 3 new columns, and I could I'm going to do and what I get back is I know I have names. But in any case, I can add the get dummies will give me the new columns, and then I can use these variables in regression. All right. Let's go ahead and we'll take a little break, and then the second half of today will be a little bit shorter, I think.
And then can you post these afterwards?
Yeah.
So the way I'm doing it is software is let's put this stuff in change. Otherwise you can just find the info, put it up there.
Yeah. I have a question for you.
So the other one is more
Work I'm working on
it's all change
building
everything.
perfect
Like,
categorized
I
emails
was
that
saying
connect from clients. You can
I
also see emails, and it's a very manual process.
Okay.
We get them on all sorts of formats and
I
all sorts of
just
things. And so I've been finding
Does that
that
make sense?
boy, I don't want to go through and like figure out all the scenarios ahead of time. It's very kind of figuring out, okay, like these emails come in this way, and I need to like parse this from the subject line and put that in the system and then categorize it this way.
Yeah.
Is it structured or unstructured?
Yeah.
Like the data, the emails.
Like is it like had like Bugzilla tag in it, or is it just like you try to learn what's in there? Is it
different-
just looking at the
different like
language?
clients, yeah, send it in different formats. So some like one client will send it in the same format generally. Like there's different ways I can count. Like some of them, maybe from a certain sender, I can read the subject line and look for a certain tag and send it to the tag. And if it has that tag, I can categorize it. And if it doesn't have that tag, I can body for different data. But I have to like parse it all.
Okay.
And so if I found that all the nodes in it, like finding like okay, like I want to categorize these emails this way, and then I think. And I write like a for statement and categorize it, and I realize, oh, I have these, so then I put it in a dictionary, and then I put it in a dictionary, right? And I'm kind of going through like iterating and refactoring a lot and stuff. Does that kind of sound like a reasonable approach?
Yeah.
I feel like it's the right way to do it, because also I don't want to, like I want to be able to come to solutions that I can supplement and like making the process easier without having to do that.
Yeah, that seems like a reasonable, like as you go along, you figure out that you did it wrong, or then you do better, you can fix it.
Or I felt like, okay, I need to do category. I don't want to keep writing functions to do that. I'll write a function that categorizes it in a certain category.
Yeah.
And I realized, oh, I want to categorize things in different categories, and update the function to pass a string for the category. Right? Like, just keep iterating like that.
Yeah.
Alright.
I just had a you keep using that term coefficient. What are you referring to?
Oh, that just means a number, like a scalar that you multiply something by.
Okay,
So
like
the
before
beta,
x, right?
Yeah, so the beta is the coefficient.
I just
So
want,
there's
that's what I
multiply.
thought, I just wasn't sure. So it's basically the number beta before x.
Yeah, it's just what we scale.
I didn't look up.
Oh, they're in the, there should be in the search folder.
Okay.
Are the empty seats, are those people that are at internships now, do we know, or?
He's said internship.
There's gonna be like yesterday or today, it was like, I didn't think my lectures were that bad yesterday.
Well, some dense material. It's hard to, this is a lot, we're going through like a lot of stuff. It's kind of hard to like make math feel like
Yeah.
cooler than like coding, so.
I'm a calculus aficionado. I've been like,
You remember, you still remember calculus.
yeah, I still have to use it. Not that it.
Yeah,
I haven't forced too much on you. The area under the curve is important, but we didn't talk about how to compute it. Well, fortunately, the next lecture has basically no math in it at all. So, and it's something that you all have probably learned on your own in John's class. So we're gonna blast through the first part pretty quickly. Yeah. So first, the next lecture is about basically where do you get data, how do you get data. So we're going to talk about two approaches, which are scraping and web APIs. So scraping, I think you've seen a little bit before, right? We basically download a web page, and then we can parse the HTML into the DOM, and then using the DOM, we can, extract the things that we care about. Okay. Beautiful Soup is not installed yet. So Beautiful Soup is a Python library for doing DOM processing. This is just an HTML file that's local, you can extract fields, kind of like the same way you would do in JavaScript. It's slightly different syntax, but you can extract tags and divs and look up stuff by ID and get things by attribute or tag type, all that sort of stuff. So I'm not going to really spend a lot of time on that. How many people ended up using Beautiful Soup for John's class? What did other people use? Is there another? Okay, and that's like a browser, headless browser or something.
I think it was some people that were using, I know like Tristan, I think was just scraping like static website. A lot of us were scraping like
stuff with like JavaScript and that kind of stuff. And so once you loaded it in Selenium, what did you do with it?
I was using it to like target things and input data. But I was using it to log into Hulu, like anonymously, like log into Hulu and like alter stuff, like add stuff and like keep it stuff.
Oh, cool.
Yeah, I found it the most useful for, I was doing airlines and I had a bunch of pop-ups and stuff that weren't always there. Sometimes it would, put up a test for me to get that.
Yeah. One student last year tried to do like flight stuff with Delta and it got his IP blocked for a while. So.
Yeah, I got blocked by American for sure.
Yeah. Which brings us to the next thing. So there are rules for scraping that are usually specified in the site's robots.txt file. So if you go to a website, so this is Google Scholar. How many people have used Google Scholar? It's like a place for funding like research papers and for whatever reason patents. But if you're doing academic research, useful tool. So this says basically, so the user agent is the software that you're using. So there's usually different rules for like Chrome versus Google Web Scraper or whatever. So different rules for if you're a robot or something else. So this says anybody is not allowed to scrape these things, but they are allowed to scrape these things. So you can't look at like citations for everything, but you can look at citations for a particular user, I guess. So these are the rules for what you can look at, and Twitterbot and Facebook. It looks like they can do whatever, or maybe they can do nothing. I don't know the syntax for this, but when you want to scrape, the first thing you should probably do is look at the robots.txt to see what are the rules, right? Because if you break the rules, you could get blocked, or you could get, some sort of legal threat or something if they're particularly upset at you. Has anybody heard of Pad Mapper? So when I was looking for an apartment a few summers ago in an internship, it gets Craigslist data and then just puts it on Google Map and then just links, so you go to the location, you click it, it shows you the Craigslist ad. They got sued, or Craigslist, I think got them shut down. They had gotten So they were not allowed to scrape Craigslist data. So they scraped Craigslist data from someone else, and there was this whole fight over whether or not they were allowed to do this, and I think they ended up getting shut down. So yeah, be careful about the robots.txt. The other things you'll see are delay or rates. So how long should you wait between queries? We'll take a look at the courses from Utah. So here's the webpage. The URL lib.request is a built-in library for it's like wget in Python basically. There is also a library called requests that we'll use a little bit later. But we're basically just going to wget this static web page that we want, and then we can process it at our leisure. So we look at what we get back from the university about the course schedule. Continuing ed classes. This is how the university describes a class on their website. We can use our DOM manipulation type stuff to extract all of the different class prefixes or subjects. And if we look at math, we see where the schedule is and all that stuff. I think I don't think we're going to go through this in too much detail unless I think I'll kind of leave it there. The beautiful soup is the library you want to use, and it's pretty straightforward. I think having worked with JavaScript, you'll pick it up. But it won't be an issue for when you have to use that question.
So we'll be doing a scraping.
We'll do a little bit of scraping. Yeah. I may tweak it. So last year, the assignment I tried to give that came from the data science course was doing something like counting stars in GitHub repos, scraping GitHub, and that turned out to be a nightmare. Just the way that the GitHub HTML is really hard to find what you wanted and all sorts of stuff. So instead, we were looking at Hacker News, which is easier to understand. So we'll have an assignment where we're going to do some classification and prediction stuff about Hacker News.
So can you talk more about the website asks you to wait before?
Yeah, so that's this delay field in the robots.txt. You'll see the crawl delay or request rate. So if you go above that, so these are probably, it says like wait 30 seconds between responses. If you go over that, then they'll probably throttle you or block you for a little while or something.
So how do you deal with that?
In code? So you might use like sweep in between requests.
So how do you know the website asks you to wait before you even do those kinds of
So I would go to the robots.txt manually and look at it to understand it. If you were writing like a Google scale crawler, you would like automatically look at the robots.txt to decide what to do. But for us, I would, we're looking at a small number of pages. I'd say read the robots.txt yourself, see what the rules are, and then try to abide by them. Yeah, any other questions? So scraping, I mean, you've done it, so not too much else to say about it. So scraping is not necessarily an ideal way to get data because it's designed to be read by a human. It's not really designed for programmatic analysis. So a more convenient way to get data, if the provider is considerate, is to use an API that's specifically designed for this. And so usually the difference is, instead of giving you back an HTML page with nice formatting, you get back like a JSON string of structured data that's easier to process. So we'll take a look at a few different APIs. So we're going to play with a cool one that gives us information about the space station, and we'll look at Twitter a little bit later. So usually we have to create an account with the API we're connecting to, and they'll give us like some crypto token to include with our requests, so they know it's from us. Twitter has that. I have not included that in the notes, so if you want to run the Twitter code, you'll have to set up a developer account with Twitter. So usually you have to, for a lot of APIs, you have to authenticate. Okay. A lot of them, they have a REST API. So REST just means that the URLs kind of describe what you're asking for. A lot of, so if it's like not a very popular service, you might have to build up this URL by hand when you want to make a request. For Twitter, there is a library that does that for you. So you pass the parameters as like a Python dictionary or whatever, and then it will format them in the appropriate API request. So this is the request library. It's like the URL lib request, but so this opennotify.org has an API endpoint that tells us where is the International Space Station right now. It returns the latitude and longitude of the ISS. So if we get, so the response code tells us if it was successful. If we look at the content, so we get this nice JSON string saying, this is the position of the space station right now. This is the current time. Pretty handy. The content type tells us what's there. We get it back as bytes. So if we want to do string stuff, we have to convert it to a string with this decode UTF-8 method. The JSON library is lets us convert this into basically a Python object, and then we can index and do all that stuff like we would do in JavaScript. Okay. Pandas knows how to read JSON. If you look at this, the table that we got is not really what we want. So this table is not super useful for us. Why? Yeah. So the latitude and longitude are really columns, and the timestamp is the index. And so it's kind of like a maybe sideways. So we can reshape this into something like this, and then we can import that into a data frame. So it's much easier to manipulate a Python object than it is, you know, an HTML table or whatever. So what we're going to do is we're going to get the space station coordinates every couple of seconds, and then put it into pandas, and then we can plot it. So what we're going to do, we're going to get the location, decode it as JSON, flatten it so that we can put it in our data frame and it has the right fields. We're going to stick it in our, we're going to make a list of these, and then we can make it, we'll make a data frame out of that list of positions. So here we go, it's moving. Kind of amazing that, I mean, this is the position of the space station. It's just easily available data to us. And so here we're using sleep to limit to pause between requests. Okay. So now if we put this in a data frame, so we're just loading this. We're converting our timestamps to date time objects, so we could, if we wanted to do more intelligent date processing, we could do that. We're indexing by the time. So we're saying that that should be our index for the table. We're converting latitude and longitude to floats. Right. So now we have the path of the space station over the last minute or so. Pretty neat. There's other endpoints here. So this open notify will tell us when the space station is going to be close to us. Most of the APIs to pass extra parameters use the query strings, that's the question mark, all that stuff. So if you use like the Twitter API, the library will automatically like take your parameters and format them and do whatever for you. But for here we can just do string processing. Also, the request library lets you pass in a dictionary, and it will turn it into the question mark ampersand stuff. So this is going to say tell me the next 5 times when the space station is going to be over Salt Lake, and it'll tell us all that information. So the next one is going to be tonight at 1 in the morning. Kind of neat. There's another API which tells you the number of astronauts. We can go ahead and query this guy. Let's see. So there are currently 6 people in space, and they're all on the ISS. Yeah, this open notify. I guess they're all space APIs. This is an example of one with no logins required or anything like that. A good one to play around with. So the next one we'll look at Twitter. So this one, you do need to authenticate. So I have my Twitter credentials I have stored in this file here. I have not included it, so you'll need to basically make your own credentials.py file if you want to follow along. And so basically, you have these secrets and tokens and stuff. Yeah. This one has a Python library that will do the formatting of your request for you, called Python. So, this is a tweet. It's got timestamp, stuff that's in it, number of faves, the tweet ID. ID is a string for some reason. Other information about the tweet, whether or not the user is verified, good stuff too. So I'm setting up my Python instance, and so here I'm just going to search for all the tweets related to hashtag NBA playoffs. So here's some of the tweets. So somebody tweeting about Drake and the Raptors. Got a whole bunch of tweets here. This is something more about the Raptors. So, I can easily grab whatever data, and it's in this nice JSON form, so I can process it easily. Okay. I wanted to look at a particular one. This is weird. I don't know why everybody's talking about LeBron James, who was not participating in this year's playoffs. As I was updating this last year, it was Cavs Warriors. I decided I think the Bucks are going to win in the East, so we're going to go Warriors Bucks for all the analysis we do below. So yeah, so we have nice JSON objects, so we can easily look at the text of our tweets and whatever else. Is that Aaron Rodgers?
He's an owner.
He's an owner?
Yeah.
Oh, okay.
Yeah, he's a part owner.
So here we're going to grab some tweets from the Warriors. So yeah, that's what the Warriors are saying. We can also, these are the dimensions, sorry. Here we're getting the timeline for the Warriors. So these are the tweets that the Warriors have made. And then we can count the number of favorites and number of retweets. So here's all their tweets. So we can do the same thing for the Bucks. And we'll just look through through these tweets, and we'll get the number of favorites and retweets. And count those up. And we can put this stuff in some data frames to start doing some analysis. So we'll have the number of Warriors faves and Warriors retweets, Bucks faves, Bucks retweets. So these are basically for each of the Warriors tweets, the number of faves and retweets for those tweets. And that is insane to me that the average tweet gets 7,000 hearts. and the 38,000 like tweet. That's pretty impressive. And that must have been like, I think we're only looking at 50 of them, so probably within the last couple of days. The Bucks, less so. Their max tweet is substantially less than the average in terms of faves. So now we're going to plot the tweets against each other, but we're going to sort them by the number of retweets, and then we'll plot so they're like increasing, so we can kind of compare the lines. Right now they're ordered by time, and so it doesn't really make sense to compare them. So what we're doing here is we're going to sort them by the number of favorites. We're going to reset the index. So now they're ordered by the way that we just sorted. So now we see that we're sorted by the number of favorites. So no fave. I don't know what tweets have no faves but 2,000 retweets. That seems pretty weird to me, but we have here's the Bucks stuff. We're going to put them both into a single data frame, and now we can plot the engagement of all these tweets. So we've sorted by the number of faves, so the faves lines are just going to go up. We see that retweets are sort of correlated with the faves, but not exactly, and that the Warriors are just killing the Bucks on social media right now. Cool. Yeah, so this is an example of using another API. There's more rules for how to use the APIs. You usually have to authenticate, but the programming experience is much friendlier because they're giving you data that's in an easily machine digestible format. So you don't have to worry about crazy formatting or anything like that. Any other questions about APIs? Cool. So the next thing, we'll just take a look at, go through an example of doing a little bit of data analysis with this one is a scraped data set from Wikipedia. We're going to look at the Olympic medalists and do a little bit of analysis on that. And just to get a sense of what it's like working with beautiful soup and all that stuff. Okay, so we're going to grab the list of multiple Olympic medalists. We'll grab the data. We'll save it locally so that we don't have to keep hitting Wikipedia to work with it. Okay, so this, now we only have to do this once. Now we can do, as much as we want, and we're not hitting Wikipedia. So we know that from looking at this, we figured out that our Olympics are in the first table element of the page, and they're numbered. So actually, maybe let's. So this is what we're looking at. All right, we're going to throw away the first column. It's not useful. This part is going to be kind of obnoxious. We'll talk about that in a little bit. Right, where we have this called the row span element. So we have this element that's actually part of multiple rows. It's going to be a big pain in our butt in a little bit. So we'll have to look at how to deal with that. Cool. So we got the names of the columns out of the first row. So the TH or the table header elements. Here is a function to basically copy the row spanning elements down to the next one. So basically for each row in the table, we're going to grab the element in that row. If the element has a row span, then we are going to grab that row span, make a new table element, and insert that element at the end of each of the next number of rows, so that we fill that in. So that kind of makes sense. So this is the kind of thing we have to deal with because this is not designed for data analysis. This is designed for nice, convenient viewing, right? So we had to do a little bit more processing. Cool. So if we do this, and then we can now we can load it into a data frame. So I'm going to make an array. I'm going to make a list of rows, and then each row is just going to have all the fields for that row. And now that I've done this propagate row spans thing, each one should have the same number. And so I have all these rows of data. I'm going to make a data frame out of it. And then I grabbed the names of each row because it was the table header. And so at this point, I can actually put everything in a nice data frame. Not perfect. I have these new lines in here that are kind of obnoxious. But I have the data looks pretty good. So that's I'm optimistic about that. So to I have to do a little bit more cleanup. So the strip function is pretty useful. It throws away any of the any spaces around at the ends of strings, end to the beginning of strings. I can map stuff to ints, and looks like another instance of having an extra space. Oh. So it looks like I have a whole bunch of extra new line characters in all these titles. That's going to be obnoxious. Actually, let's go back and clean this up. So I have all these new lines here in my headers. So what can I do about fixing that? I can strip them. So let's go up here where I get my headers. So I'm going to strip. That should be good. And now I will redo all this stuff. That looks a little bit better. That looks a little bit better. That looks a little bit better. And now I can do now I can plot the number of gold medals by country and do all sorts of fun stuff like that. So I have converted my HTML table into a data frame object that I can do all this sort of manipulation with. So some tricky stuff I had to deal with here. White space, so strip is your friend. The row span stuff was a big pain to copy that element into each row that it was part of. And then after that, it was pretty smooth sailing. And we see that America has by far the most golds from multiple Olympics. So, doing great. So that's like Michael Phelps and Mark Spitz, and who else? Who else is getting on these? Oh, Soviet Union up there too. Looks like swimmers and gymnasts. And winning the biathlon 13 times seems pretty impressive. All right, so yeah, it's kind of a quick whirlwind tour of how to get data to analyze and how to massage it into a form that is suitable for analysis. Right. So yeah, again, when scraping, make sure you look at robots.txt to see what you're allowed to do with it. If the rules are strict, I would say, go there with your browser, save it, and then do your analysis offline if that's possible. If there's an API, much better. It's easier to work with that kind of data because it's in JSON and it's a lot more friendly to work with. Right? Yeah, and then we can massage it into nice data frame format and do all of our analysis there. Okay, so I think we'll end a little bit early today. Now would be a good time to take a look at the next homework and get started on that. So it's analyzing a data set of Salt Lake real estate data. So, yeah, any questions? Right. See you tomorrow. Varun will be back, so you'll have databases tomorrow at 8:30.